So welcome to the 24th Climate Intervention Virtual Symposium. Our first speaker is Michael Diamond, professor at Florida State University, and he's going to give us an overview of marine cloud brightening. The chairs is yours.
Awesome. Thank you so much, Ilaria, and thank you to you and Matt for inviting me to talk today. Really excited to talk about marine cloud brightening and particularly this question that I've been focused on for the past several years of to what extent shipping, international shipping, is a good analog for marine cloud brightening, or to what extent what we envision doing with sea salt spraying would be totally different in terms of the cloud physics. Since we do have a smaller audience today, it's probably feasible that if you want me to stop at any point and have a question, just raise your hand. And happy to turn this into a little bit more of a conversation.
Yeah, thank you, Mike.
So, first of all, I always love starting with an image like this. I'm also specifically this image just because it's so cool. This is not a satellite image. This is a digital photograph from the International Space Station, taken by an astronaut. And what you could see here, this is a low-lying, mostly stratiform cloud deck that's being formed off the coast of Alaska. The Aleutian Islands are some of what you could see up here. And something you can see within this cloud deck are these streaks of what almost look like these filled in, nice kind of like milky white lines going through the cloud deck over here. And you could theoretically go back and trace the beginning of each of these to an individual ship. So these are ship tracks. They're formed from the interaction between pollution from that ship's smokestack with the overlying cloud deck. And as we'll see here, we've known about these and have used these in studying the science of how clouds affect climate for a really long time now. So we first learned about these ship tracks or quote unquote anomalous cloud lines all the way back in the 1960s, pretty much the very first satellite imagery, weather satellite images we had from the Tiros generation of satellites. We had already picked these out. This guy Conover, who wrote the first paper about this phenomenon, he's an Air Force guy, so his mind immediately jumped to, oh, maybe these are Soviet missile um, tests or ship smoke screens or something like that. The reality is a lot more banal, but scientifically useful in that these are a result of ship pollution mixing into the cloud. Some of the smoking gun evidence for that was found all the way back in the 60s, where here this little wind barb is actually an individual ship position, and you can see the ship track very clearly emanating from that point. And the way this works is all clouds that form in the atmosphere have to be seeded by some speck of dust or smoke or pollen or sea salt in the atmosphere. Under Earth-like conditions, water vapor cannot just condense upon itself to form a cloud. We do not experience supersaturations like that on Earth, at least in the lower troposphere. Um, so imagine you're out over the remote ocean. There's not much pollution around, right? The only kind of particles in the atmosphere are maybe what's being kicked up by a couple of waves over the ocean. So imagine you have some amount of liquid with which you can build a cloud. Really, your only choice is to build a cloud with a relatively small number of relatively large drops. Now a ship goes by or the winds shift and you start getting air that's coming from a polluted continental area. And now you have a bunch of these little cloud seeds or aerosols floating around. You could take that same amount of liquid, distribute it out amongst a much larger number of smaller droplets. That is making much more effective use of the surface area for that given volume of water. That gives the clouds a higher albedo, just a fancy way of saying reflectivity. You're reflecting more sunlight to space, therefore less sunlight is warming the Earth, therefore you're cooling the climate. We call that the Toomey effect. The science behind this was pretty much all described by Sean Toomey in the 1970s, and it's a relatively straightforward physics.
Oh,
Oh, hi, Sean. Um,
So
no worries. If you have questions, feel free to peep up. Um, Imagine you have the same amount of liquid is doing a lot of work in that thought experiment, though, right? These clouds can adjust and actually change the amount of liquid, and that's going to have a very important effect on their brightness as well. So, what happens when you have a bunch of little droplets? It's actually much harder for these to collide with each other and grow to the size at which they form precipitation drops, or drops that basically fall appreciably from their own gravity. That means you might have clouds that stick along around for longer or hold more liquid water within them, giving you even more cooling. For a couple different physical reasons, you could also have an effect where the clouds get better at drying themselves out through turbulent entrainment at the cloud top. That would tend to decrease cloudiness and lead to a warming effect. So if you ever wonder why if you've ever seen that IPCC chart of aerosol cloud interactions and the arrows go from basically zero to offsetting 80% of CO2 forcing. How these adjustments influence the Toomey effect is a lot of what's going on there. These ship tracks were instrumental, actually, in formulating and testing a lot of these hypotheses about cloud adjustments. So I'm showing here an image from a paper that did some of the first aircraft measurements of ship tracks back in the late 80s. And you can see here in the droplet concentration, you get these two spikes where the aircraft sends these two ship tracks. And they happen to notice in this paper that you got some liquid water content spikes at the exact same time. When they looked more detail at the droplet size spectrum, where you have small droplets over here, large precipitation size droplets down here, the solid black line is the ship track. The dashed line here is some clean clouds right next to it. They also noticed that even though you had more drops in general, especially among the smaller sizes, you basically lost that whole drizzle mode. And that became the inspiration for the Albrecht effect, or Bruce Albrecht's famous paper that, if you've ever heard of the second indirect effect or the Albrecht effect, that lifetime effect of reducing precipitation and increasing cloudiness. That's where that all comes from. We now know it's a little bit more complicated than just that happening, but ship tracks were actually the inspiration there. Ships were also some of the first widespread systematic evidence that you could get reductions in liquid water in these clouds. So one great example of this from Jim Coakley in the early 2000s was looking at a bunch of ship tracks from satellite and noticing that not all of them were brightening at the rate that you would expect as the cloud droplets got smaller. And for that to be true, that means that some of those clouds had to have, and some of them were even darkening. That means you had to have reduced liquid water in those clouds as a result of the aerosol for that to kind of work out physically. So we've known about those two effects for a long time. We've also, since the late 60s, had at least the inkling that you could do this on purpose. So as kind of almost a throwaway line at the end of his paper, Conover says that if you wanted to, cloud enhancement to increase the albedo over large areas would be artificially possible. So I would consider this the first mention of an MCB-like idea in the literature, although the modern form of it comes, to my understanding, independently from Latham in 1990. So the big question for us now, I think, becomes, are these ship tracks truly analogous to MCB? And I'm going to address this in three parts. One, do ship emissions themselves actually exert a meaningful radiative forcing, or is it more just a kind of useful example? And if they do exert a meaningful radiative forcing, how much of it is from these clearly defined tracks versus how much is it from kind of long-range transport of these aerosols where it's all smeared out? Some of y'all have probably heard of the recent International Maritime Organization regulations. Ilari and others have written great modeling, also observational papers about that. There's been lots of interest in could this be a reverse termination shock that's kind of a real life proof of concept of MCV. So I'll address that next. And then finally, how much do the size and composition differences between shipping aerosol and sea salt spray matter? So how much can we actually use ships as a one-to-one proxy for what we would envision doing with salt under MCB? And particularly, I'm interested if the soot absorption that also happens in these ship tracks could explain some of that decreased liquid water content that Jim Coakley found, and others have since found quite a bit. So first of all, do ship emissions exert a meaningful radiative forcing? And this is a more challenging question than I would have expected. So, until relatively recently, if you went from an observational perspective, you would have gotten a solid no. So this is, I think, a great example of that. A paper from Schreier and colleagues in 2007, where they very laboriously went through and cataloged visible ship tracks in satellite imagery by hand, and basically picked out all those tracks, picked out how bright they were compared to background clouds, and then got a global forcing out of that. And the global forcing they get is zero point 0 or 0.0005 watts per meter squared. Yes, half a milliwatt per meter squared globally. In some regions of particularly intense shipping, like off the Pacific coast of the Americas here, you get maybe about, negative 0.05 watts per meter squared. Um, this is negligible. This rounds to zero, genuinely. Um, so maybe this is just kind of like a cool party trick, right? We get a couple great satellite images. We can motivate all of our MCB talks, but it turns out this doesn't really scale up to anything globally. But if you put sulfur emissions into a global climate model, and here's an example from that exact same year, Axel Lauer and colleagues, same also in 2007, put three different plausible sulfur inventories from shipping into a global climate model, Eckham in this case. And based on which inventory you get something between negative zero point zero 0.02 and negative zero point zero 0.06 watts per meter squared. For context, that's about 10 to 40% of the total human cooling effect from aerosol on the climate in that model. So something really, really substantial from ship radiative forcing. And if you look at this, right, we have a model observation discrepancy of 2 to 3 orders of magnitude from those lines of evidence. So something's not adding up. And this is actually a case of the models being much more trustworthy than the observations, or at least how we were using the observations in that case. So instead of trying to construct a shipping forcing from the bottom up by counting all these individual ship tracks, we could go from the opposite direction. What if we go from the top down and try to look over entire shipping corridors? So what I'm going to show here is from this Southeast Atlantic shipping corridor. You see it's relatively isolated over here, going between the Cape of Good Hope around South Africa to Europe, one of the major routes between Europe and Asia besides the Red Sea. And we could see in the middle of this stratocumulus area right over here, this is one of the world's 3 main stratocumulus stacks right off the coast of Namibia, Angola over here, this really suspiciously linear feature. And here I'm showing satellite-based estimates of cloud droplet size. So the yellower colors imply smaller cloud droplets on average. So I'm not going to go into the details. This talks a little bit just of a whirlwind tour of this question. But my group for a few years now has been using a method to use clean areas on either side of the shipping corridor to create a statistical counterfactual and treat the difference between that statistical counterfactual without shipping and what we actually observe as the causal effect of shipping. And if we do that, we see a pretty strong signal of smaller cloud droplets, and therefore brighter clouds right within the shipping corridor in this stratocumulus stack. If you actually convert this to radiation, you could either do this from using some known physics with the cloud properties or looking at radiation-based satellite measurements themselves, which I'm actually showing here in the black and purple. But you get something on the order of a couple watts per meter squared in the region. And that actually agrees really nicely with the values from global modeling. So in terms of that order of magnitude estimate, at least, this top-down method actually reconciles our observational and modeling based estimates and suggest that the models are closer to the truth in terms of the total forcing they're getting from shipping globally. So we can answer that question. Ship emissions do exert a meaningful global radiative forcing, probably something around 20% of the total, more or less. Um, so how much of that is actually contributed by clearly defined tracks? Is that what I'm catching in my top-down method, or am I also catching a lot of diffuse, kind of blurry stuff that a human or a satellite would never pick out? So we can test that now. Schreier and Matt Christensen and others have made these really great catalogs of hand-tracked ship tracks. But in the last few years, independently, Tianli Yuan's group and Duncan Watson Paris's groups have created these great machine vision, so neural net methods detecting individual tracks, and they find um, one or two orders of magnitude more ship tracks than you can possibly get from that abuse a grad student manual method. So let's go ahead and take the ship tracks derived from these machine learning methods and compare that with my top-down constraints from the statistical method I just introduced. And a couple months ago, we published a paper looking at this in Communications, Earth and Environment, led by Tianli. And it turns out that these visibly detectable ship tracks that produce beautiful satellite imagery really are just the tip of the iceberg of shipping radiative forcing. So in the top row here, this is just what I showed before, except instead of droplet size, I'm now showing droplet number, but same thing. Yellower implies more number, brighter clouds. We get about a 10% increase in cloud droplet number through this top-down statistical method. Based on detections with machine vision, we get detected tracks around 1 to 2% of the time in this region. If you multiply that by the average in-track versus background difference in cloud droplet number that they find, you get an inferred climatological enhancement of a little less than 1%. And if you go through the math of this and you could do it on ND, you could do it on radiative forcing, pick your variable. The top-down corridor approach is consistently about 20 times greater magnitude than trying to construct a bottom-up climatology. So it really does turn out that only a small minority of this total forcing is being contributed by clearly defined tracks. A lot of this is happening as the ship track dissipates and spreads and becomes harder and harder to disentangle from the background, or basically becomes indistinguishable from the background. So with that, now that we know that ship emissions do exert a meaningful radiative forcing, the question becomes, in 2020, we just cold turkey 80% reduction in sulfur over the open oceans, January 1, 2020. Did that plausibly result in a reverse termination shock that maybe was also responsible for some of the very rapid warming we've seen since 2023 or so? So along those lines, this middle row that I showed earlier is just those 3 years pre-IMO, and you can see it's a little bit noisier, but you get that same suspicious line and pretty clear shipping signal in the shipping corridor of smaller cloud droplets than you as you do in the climatology. If you look at the 3 years after IMO 2020, that basically disappears. And you get this kind of noisy, maybe you have a little bit of statistical significance down here, but a lot of that effect is gone, which is great. We understand cloud physics. That's awesome. But the question becomes this 80% reduction in sulfur. Did we lose 80% of the cloud forcing? Did we lose close to 100% of the cloud forcing? Did we actually only lose 10 or 20% of the cloud forcing because things are really nonlinear? That's really hard to say. And now that the signal's so small, that's even harder to say because, yeah, it's actually really hard to get at exactly how much ships are now perturbing these clouds with these much less efficient cloud seeds with this much reduced sulfur load. So, we have a little bit of an interesting natural experiment within a natural experiment to help us out here. Um, In November, or October, 2023, we had the beginning of the Israel-Gaza war. We're gonna have to, keep all of our Mid-East wars with shipping implications straight, because there's now quite a few of them. But this was the first one, if you remember back to 2023. Um, as part of that war, starting in this November 2023, the Houthi militia based out of northern Yemen here started attacking ships transiting the Bab el-Mandab Strait um, down here. So in 2024, just in these 2 months, September, October, you could actually see all of these red dots are where a militia attack on a merchant vessel took place. And you could imagine this had a pretty big effect on the willingness of shippers to go through this Red Sea route via the Suez Canal between Europe and Asia. And you can actually see here, this is retrievals from Tropomi of nitrogen dioxide columns. You actually can see the shipping corridor in most years just as this really clear bullseye of NOx in the middle of the Red Sea here that basically disappears in 2024. You're losing the vast, vast, vast majority of large ship traffic through the Red Sea as a result of these militia strikes. But those ships have to go somewhere, right? Europe still wants to sell its stuff to Asia or buy stuff from Asia. Asia still wants to sell stuff to Europe. So where do they go? They go around the Cape of Good Hope. So if you're really eagle-eyed in 2023, you can kind of make out that shipping corridor we had looked at before over here, but you could see it much more cleanly here in 2024. So it turns out that ship traffic around Africa is going up by factor of two, factor of three maybe, because of this conflict. So if we think about our logic chain here, we have militia attacks on a shipping route on the Red Sea. Over here, I'm showing the change in cloud droplet number within this shipping corridor over Africa that I showed before. So normally it's about 10% pre-IMO 2020. After IMO 2020, it becomes indistinguishable from zero, but probably something around half that. But again, hard to say because the signal's so weak now. In 2024, it jumps back up to what it was before. But it's doing that with much greater shipping activity as measured by this NOx perturbation. NOx is not related to the shipping composition. You generate the NOx by burning fuel at really hot temperatures. Doesn't matter what the fuel is. This is a pretty good proxy just for shipping activity overall. So this is suggesting we have much greater shipping activity in 2024. And if we normalize this, so get a sense of the cloud altering ability of ships per ship activity, we find about a 67% reduction, and actually quite statistically significant and very distinct from zero between these 2019 values and 2024. So about a two-thirds reduction in cloud microphysical change, and therefore probably also forcing, although it's a little bit hard to go straight from the Toomey effect to total forcing because those adjustments can be quite nonlinear. So I don't want to overpromise on that. What does this mean for global temperatures? Well, from global models, if you put these shipping emissions into a global model, you get a forcing of about 0.1 watts per meter squared. This could lead to something like an zero point 0.5 to zero point 0.1 increase in temperature by mid-century. That's meaningful if we're thinking about trying to keep temperatures below the Paris Agreement reach goal of 1.5 degrees Celsius. However, it's probably not something that we would expect to just pick out of the global temperature record. Duncan Watson Paris has a really nice paper on this using the CSM2 large ensemble, showing that this is pretty solidly within the noise of internal variability. Different papers, so Ilaria and Matt's papers are framed a little bit more in terms of this has maybe increased warming by a couple of years. Duncan's paper is framed more in terms of this is within natural variability. My answer to that is yes. I think both of those things are true simultaneously. This probably has accelerated warming by a few years, but internal variability is also quite large, and that's not something we would expect to just see um, through a simple global sea surface temperature plot or something like that. Okay, so we have that. Recent regulations are they did likely reduce shipping rate of forcing, probably by order two-thirds would be my best first order guess, but it's unlikely that's detectable in global temperature, at least without very fancy statistical methods. How much do the size and composition differences vary between shipping aerosol and sea salt spray? I'm particularly interested in soot absorption here because there are a couple of papers now suggesting that rather than being an entrainment effect with smaller and more numerous droplets in the entrainment interfacial zone at cloud top, it's actually soot from ships that is absorbing sunlight and burning the clouds off. That might actually become an even bigger concern after IMO 2020 because when you're using your heavy fuel oil, so pre-IMO fuels, most of the aerosol is sulfur. Post-IMO, most of this is now organic and black carbon and probably some brown carbon in this organic fraction. So let's simulate this. So these are very much hot off the press, a preliminary view LES analysis done by my former postdoc, Prashant Prabhakaran. He just moved back to India and is starting a faculty position there. Excuse the relatively preliminary nature here. But we're taking a real observation of from satellite, and also we sampled some of these clouds in the Oracle's campaign back in 2018 of a ship track going through open cellular convection over here. You can actually see it quite nicely there. This is just a plan view from the SAM modeling that we're doing to first order, right? The smell test looks like it's doing a pretty good job. If we look at the change in liquid water path between the or the ship affected cloud over here and the unaffected clouds over here, we're seeing all of the different perturbations we've done here. See some decrease in liquid water. Don't worry too much about all these bazillion different colored lines. Just focus on the green and the pink. The green is our accumulation mode, quote unquote, sulfur track. So think of that as the pre-IMO 2020 type fuel. The pink is the exact same thing, but we're giving it the absorption properties of smoke. Actually, relatively highly absorbing smoke. So it's absorbing a good amount of sunlight. So a pretty strong effect. We see basically no effect over here in the liquid water path. So this is still, I'd say, a little bit preliminary, but I'm willing to go out on the limb here and say that from what I've seen of our other results so far, there's about no effect of including smoke absorption on thinking about these cloud adjustments. This really is a microphysical effect, and therefore, if we're looking at cloud adjustments in ships versus cloud adjustments that we'd expect for MCB, they're probably a pretty good proxy. Something we are seeing, though, are much bigger differences in cloud adjustments based on sea salt size and the emission rate. And because of that, I'm going to leave it here, but I just want to do a really quick shameless plug for the new paper that Sarah Doherty and I, as well as our co-authors Rob Wood and Haruki Hirasawa, have published in AGU Advances yesterday. So again, hot off the presses, where we're looking at what a field program for teasing out the physics of marine cloud brightening and what could we only understand by going out and doing some perturbative studies in the field as opposed to using modeling and using the natural analogs that we already have. What can that tell us? So with that, I am excited to take your questions.
Thank you, Mike. I didn't interrupt you because I'm afraid that Robert is not going to join. And it's my mistake because I didn't know that the US last week was entering the daylight saving time. So I probably provide the wrong time. So we have time for several questions for Mike, but we can always end the meeting earlier. So if there are any questions from the audience. Okay, I don't see anything for now, so I'm gonna ask my question. I'm not sure I really understood the last part. So if there's gonna be a deployment of marine cloud brightening, do you think that suit will affect that? So should we think about how much sea salt we have to inject based on uh, how much soot we can inject because of ships?
Yeah, yeah. Sorry, you didn't explain the last, or you didn't probably understand the last part because I did not explain it very well at
No, no,
all.
no. It's it's
Um,
it's my fault because I was checking if Robert was
oh,
attending, and I'm sorry.
no worries. So, and sorry, I think the set stuff kind of seems like it came out of nowhere. Right now, there's a little bit of a controversy in the shipping literature about how much of the negative cloud adjustments we see, so the negative liquid water path effects we see in ship tracks come from the soot that also, so when ships burn their fuel and have their emissions,
Hmm.
a good chunk of it is basically carbonaceous gunk, for lack of a better word. So actually, for both now and in the past, pre-IMO, what's happening first is you're burning still relatively dirty fuels and creating Aitken-size carbonaceous gunk. When that fuel had a very high sulfur content, you weren't emitting most of that as SO4, you were emitting most of it as SO2. And within the boundary layer, it's getting oxidized to
Hmm.
sulfate. And rather than new particle formation, it's probably depositing on those carbonaceous pre-existing aerosol and growing them to larger Aitken or accumulation mode sizes and also making them really hygroscopic. So the question becomes, one, you do have this is now a mostly sulfate particle, but it has a black carbon core. The sulfate might actually lens, so it still could be quite absorbing and produce quite a bit of a semi-direct effect. Maybe. Back of the envelope calculations I have done suggest this shouldn't be large, except in very, very concentrated plumes, but especially fresh plumes can be very, very concentrated. Um, Post IMO, you still have the carbonaceous gunk, and you actually might even have a little bit more carbonaceous gunk than before. You just don't have the sulfur that's depositing on it. So the question is then, when we're looking at the cloud adjustments in these ship tracks, are we actually seeing something that's based on this carbonaceous gunk that we would not have from sea salt? Sea salt would be almost perfectly scattering.
Hmm.
Single scatter albedo, almost exactly one. Um, So the answer from the large eddy simulation results we have so far, and also just from some of the back of the envelope calculations I have done, seem to suggest that no, this absorption effect really is too small to account for these satellite differences we've seen. This could be a really big, this would really challenge if it were true that soot in ship tracks was a major factor here would
Okay.
be a huge challenge for using ship tracks as analogs. About one third of manually detected ship tracks actually show cloud darkening. And if that were a semi-direct effect that wouldn't exist under marine cloud brightening, you would actually massively underestimate marine cloud brightening's efficacy using the observational record. I don't think that is true. I actually think that shipping forcing and marine cloud brightening the main source of non-analogousness, if that is a word, between them is really going to be the emission rate and the size, if you had to ask me
Okay.
right
Okay. Okay. Thank you.
Um,
Um,
yeah,
yes,
could
Mike, go ahead.
um, so these ship tracks that are shown on the one you have these clearer areas on the side,
now.
which I guess is from what overstimulation of the CCN concentration or something. I guess what I'm wondering is a little is sort of is it possible that elsewhere there's just too much CCN being put in that you're not getting clouds? Um, so that as we, reduce some of these emissions in various areas, that we start getting more clouds. That's sort of one part of the question. And then the other part is, what about all the emissions on land and the emissions getting carried out over the ocean? There's sort of efforts on trying to clear up and reduce emissions over land. is that going to affect the cloud cover over oceans as well?
Yeah, two fantastic questions. So I would say it is. You have to be quite polluted to get to a point where I think that adding aerosol would actually reduce cloud fraction. Most of the evidence we have right now suggests that adding aerosol, if anything, increases cloud fraction in clouds that would have been naturally drizzling, and that situation may actually become more common as the background aerosol concentrations decrease because of general broad-based air quality policies, especially over land. The clearing you're seeing in the flanks over here of these ship tracks is something that's been diagnosed in models and seen in some satellite images for a long time now. This is probably a dynamical effect. Um, of just basically actually changing the circulation and invigorating updrafts within the ship track and some downdrafts outside. We have some suggestive evidence that the extent of that clearing next to the ship track is a strong function of the emission rate. So as I mentioned before, that emission rate might wind up mattering quite a bit more than the composition changes. This is a big problem for our bottom-up estimates, though. So if you tried to take this ship track and estimate the in-track versus out-of-track properties and infer a cloud fraction change from that, you would say that this ship track here has massively increased cloud fraction. Versus if you took the broader view and maybe averaged over this box, maybe cloud fraction's exactly the same. It's just being redistributed now. So that is a big challenge for us in terms of how do we quantify these adjustments. To your second question, we actually are seeing some effects of these broad-based air quality policies, both off of China, especially since 2013, has seen really massive reductions in sulfur dioxide. The U.S. East Coast as well, though, since 2000, or over the case of MODIS remote sensing since about 2000. Knut von Salzen has a really nice paper from a couple of months ago in, I believe, Nature Communications, looking at this off of the east coast of North America and Eastern Asia as well, showing that you are seeing likely cloud dimming as a result of this decrease in aerosol from land-based advection.
So if I can ask one more, if you were
Yeah.
trying to do marine cloud brightening, it would seem that a key question you have to know to do something well would be to have current observations at a point on a continuing basis at a lot of points to know how much to put in. Is that true, or can you just put in a relatively low amount and that will help in any case? I mean, so how precise would observations have to be if you're going to try and do large scale cloud brightening?
That is a fantastic question. And if you know anyone with a program who's looking to sponsor some student work where we're really interested in actually sticking a student on this and thinking about this detectability question really hard. So I'm going to do another shameless plug for our new AGU Advances paper. We've been trying to put in a lot of work into thinking about for each of these tests at different scales. So thinking about how the salt plume would disperse all the way to how clouds would respond in a single track. Um, what kind of aircraft or drone or satellite um, resolution, types of measurements, etc., would you need to have detectability at different scales? And the answer is going to vary depending on what your question is. So if you want to track cloud microphysics, that is going to be a lot easier than tracking top of atmosphere albedo. And that's going to be a lot easier than tracking how cloud perturbations in a certain area are changing precipitation in another, or temperature, either locally or globally, with the latter ones probably requiring something like already being at a deployment scale to be able to get a reasonable observational estimate for. Um, so sorry to punt that a little
Yeah,
bit, but I think it's a really important question that we need to answer on the observational side. What kind of observing system would we need? But it's not going to be possible to answer that question without defining clear goals of what are our objectives for what do we want to be able to detect and at what time scale.
So if no one else is asked, I'll ask one more. So the Australians are trying to do marine cloud brightening over the Great Barrier Reef.
Yeah.
And that notion is to do local intervention to try and offset key impacts or something like that. That seems much more feasible as a proposed idea than trying to do it globally, where you really would have to have a large scale observation, widely spread observation. Maybe you can do it from satellites, but or something, but that one would be able to do to determine local conditions and get perhaps optimal amounts or something of CCN injected. So the
Yeah.
regional things might seem easier to do and accomplish than global things.
I totally agree that regional things might seem easier to do. The big question for me becomes, are the clouds going to cooperate? Because we don't have the right type of clouds everywhere we'd want to do it. So in particular, the type of clouds that we are extremely certain that we can get some level of perturbation, and I would probably go out on a limb and say that we can get a negative forcing from are these stratocumulus clouds. So if you look at Tianli's image here of these ship tracks, the gray contours here, I forget if they are, okay, this is going to be low cloud fraction, I believe, or maybe just total cloud fraction. But either way, you can see here that you have some of these bullseyes, like off of the Southeast Atlantic here, off of Peru over here, off of California, especially. These are these really cloudy areas where we have these very overcast stratocumulus decks, and you can see in terms of where we're able to get a good signal from these machine vision methods of where we see ship tracks. Those are bullseyes. We're very certain about those. If we look over here at the Great Barrier Reef, we do not see ship tracks there. Unfortunately, our second speaker is not able to make it right now, and he was going to tell us about some modeling work that suggests you do still have
Yeah.
a sizable effect there. In my group, we're doing some similar studies right now, thinking about whether or not this might be possible for Florida's coral reef, in particular around the Keys over here. But both of these are trade cumulus regions, and we have, I think, good dynamical reasons to believe that trade cumulus clouds are better buffered against modification by aerosol than these stratocumulus clouds are. And it's a big open research question about whether or not you can actually get a good cloud forcing out of these systems. That said, we also have this concept of marine sky brightening. What if you just go out and spray super reflective sea salt? It'll require a lot more mass. The salt you want for that is a lot bigger than the salt you'd want to be cloud seeds. But if you're thinking about something like the Great Barrier Reef, something that's so valuable, even valuable in the dollars and cents terms that economists would want to talk about, it might be worth it, even if you can't affect the clouds, just to do some kind of essentially sky misting type thing. Um,
Yeah, that was clear sky stuff. Yeah,
yeah,
yeah. Okay. Thank you.
you're welcome. Thanks for the great questions. Oh, and thanks
Okay.
to Sarah for putting the Canute's paper in the chat.
So I was texting Robert, and unfortunately, yes, there was a misunderstanding about the time, and he cannot join. It would have been great after your amazing introduction to have him. Let's see if we can do it next month, in a month and a half. But yeah, Mike, you were great. You covered the whole hour, and so I don't feel ashamed that I don't have a second speaker. Um, Yeah, I want to thank everyone for joining us. So yes, we will probably have the next meeting in 1 month and a half. It's gonna be the same time if Rob is gonna present since he's in Australia and this is the only available time, or if we have again European and American presenters, it's gonna be back on Friday at the usual time, afternoon or morning, based on if we are in Europe or US. Okay, thank you again. See you next time.
Thank you so much
Bye.
for organizing. Bye.
Bye.